Hello everyone, welcome to this introduction to BioTherm, a computer model to simulate the production and transport of biogenic heat in soils from natural source and depletion processes. My name is Julio Cimbron. I am with E-Flux. I have been working with this model for 3 years, learning from it and improving my understanding of biogenic heat and natural source and depletion. At this point, we are making BioTherm available to the community at large. It is in beta test, so there are a few things that need to be ironed out. Still, I believe BioTherm will help users formulate their conceptual site models and the effect of biogenic heat on them. I am going to start off today by explaining how BioTherm works. Then you will get to try it yourself. First, I want to review some NSZD concepts. This is a conceptual model of NSZD reactions in the vadose zone. Many of you will be very familiar with this, but we will repeat them for completeness. The idea is that NSZD processes proceed by different degradation pathways, depending on the availability of electron acceptors. At shallow depths, biodegradation occurs anaerobically, and in the absence of external electron acceptors occurs through methanogenesis. Methanogenesis generates methane and CO2. These two byproducts are gases and mobile in the vadose zone, so they move away from where they were produced. As methane encounters ambient oxygen, it quickly breaks down into CO2. In the end, most of the contaminant biodegraded through methanogenesis shows up at the ground surface as CO2. And of course, you can have shallow contaminant undergoing aerobic biodegradation, breaking down directly into CO2. The propagation of heat follows what is called the heat equation. The heat equation describes temperatures in soils with depth and time. It is mathematically identical to the diffusion equation, except that it describes temperatures instead of concentrations, and the proportionality constant, alpha, is called thermal diffusivity instead of being the diffusion coefficient. In order to solve the heat equation, you need to define the alpha value, which depends on soil-specific properties. You also need boundary conditions, for example, ambient and groundwater temperatures. In the presence of reactions that release heat, the heat equation needs to include such internal heat generation rates. If you know this, the heat equation is relatively easy to solve. The heat generation rates in the heat equation come from the natural source and depletion related reactions. Because the heat of reaction is stoichiometric, if you can determine reaction rates, then heat generation rate can be calculated. The inputs for BioTherm include biodegradation rates from laboratory data and their dependence on concentrations of contaminants and temperatures. You also need site-specific data, including depth to water and soil properties, ambient and groundwater temperatures, as well as contaminant distribution profiles. The outputs of BioTherm are soil temperatures and natural source and depletion rates. Some advanced features of BioTherm allow you to analyze these basic outputs further, for example, to explore how to use temperatures to estimate natural source and depletion rates. This is called the thermal gradient approach. In graphical form, these are some key inputs and outputs. For inputs, we have here the contaminant concentration profile, groundwater temperatures. In this case, there's variability throughout the year for these groundwater temperatures in a range of almost 20 degrees. We also have ambient temperatures. In this case, these ambient temperatures come from a nearby weather station. And the model outputs are the color maps of soil temperatures and soil concentrations for the time of the simulation, in this case 3 years. In the next few slides, I will explain how this looks on BioTherm's website. You can access that through E-Flux website at soilgasflux.com, or you can access it through biogenicheat.com. Watch this video until the end, and then you should be able to try this for yourself. Go to this login screen and input the info printed on the top of your page. For this presentation, use our guest login account info@soilgasflux.com. This ID and the password are on the top of the page with case studies. The first time you log in under your own account, you will be asked to fill up your profile information. After you register, you will receive an account validation code by email. After you log in, this is the screen you will see. You will see previous results over here. And on the left, you will see your profile information and a button to create a new run. You can also create a new run by opening as a pre-saved run and cloning it. This is what we ask you to do today for a quick demo. BioTherm includes 9 input forms. We mostly will focus on the first 3 input forms, where you will enter the site-specific parameters, including elevation, groundwater elevation and contaminant concentration data, groundwater temperature, soil surface temperature. I call all of these key input forms. There's a next page button to flip through different input forms. This is how the first input form, called general parameters, looks like. This includes the length of the section being modeled, typically the groundwater table. It also includes the soil thermal properties of thermal conductivity and thermal diffusivity, alpha and conductivity. The graph on the right shows reported ranges and is not part of the input form, but is available in the user manual. Simulation time is the length of time of the simulation. I typically do multiple year simulation, because the output of the first year carries some error from the assumed initial temperature profile. This form includes the location and width of the aerobic-anaerobic interface. For the case studies, I have got this information, which is available from field measurements. You can also make estimates from models such as BioVapor. This selection of the aerobic-anaerobic interface is very important because it determines where the heat from methane oxidation is released. This form includes the heats of reactions as well. I suggest leaving this input as the default values. In addition to the input forms that I just explained, which need to be adjusted to site-specific parameters, there are 5 additional input forms that I consider advanced. I recommend users not to change these advanced features from the default values until they have developed some familiarity with the model, as they are advanced features. For this reason, I will not explain this in detail. One exception is the input rate losses. These ones I will explain in a bit more detail, as they are fundamental to understand how BioTherm calculates biodegradation rates. I recommend users to use default values unless they want to calibrate the model to match field measured rates, or if they have a very specific purpose in mind. This slide describes the dependence of reaction rates on concentration. The Monod equation is how we understand microbes degrade contaminants used as carbon sources. It states that at high contaminant concentrations, microbes degrade contaminants at a constant rate. This is known as zero-order kinetics. At low concentrations, microbes degrade contaminants at a rate that depends on concentration. This is known as first-order kinetics. Monod kinetics need two parameters. These are specific values reported in the literature for methanogenic biodegradation of naphtha at 22 degrees C. Of course, you need specific values of Monod kinetics for each type of reaction. The values for aerobic degradation of petroleum have been found to be similar to those under methanogenic conditions. This is from a paper from Professor Meyer's research published in 2010. As far as the methane oxidation goes, it has been shown that this reaction happens much faster than the biodegradation of petroleum. As reported by literature, BioTherm assumes this is an instantaneous reaction happening right at the aerobic anaerobic zone. What about the effect of temperature on biodegradation kinetics? It has been shown that biodegradation is strongly dependent on temperatures. This particular dataset is from published literature and indicates experimental biodegradation rates of methanogenic microcosm studies incubated at different temperatures in the lab. If you combine this temperature dependence with the concept of monod kinetics, you get a family of monod curves, one for each constant temperature. This family of monod curves enables to make predictions of local biodegradation rates based on local soil temperatures and local soil contaminant concentrations. BioTherm enables extrapolating this knowledge to field conditions in order to estimate field NSZD rates. The last four input forms relate to advanced features. I recommend that for beginners, these parameters to be left as in the default case. I will briefly explain what these features are about. The heat source input form refers to providing supplementary heat to the soil to enhance NSZD rates. You can do that as a constant rate across a predefined thickness in the soil, or you can enter your own rate that is variable with elevation. We also have input forms for thermal gradient analysis parameters and background parameters. These input forms 7 and 8 are used to make estimates of the thermal gradient based rate of degradation. The last one, if you have field data, you can enter it here, and this is just to be plotted for comparison to field measurements. Obviously, these input forms 5 and 9 can be used in combination to calibrate the model. The base case is simulating a particular location at the Bemidji site. The data is available from the literature. The depth to groundwater is 7 meters. The average groundwater temperature is 9 degrees centigrade. Ambient temperatures are available from a nearby weather station. The soil concentration at the chosen location is shown here on the right, as well as the location of the aerobic anaerobic interface within this elevation. So once you have input all the data, click on the green Submit button. BioTherm will run. It will take about 2 minutes to run unless the server is dormant, in which case a first run to wake up the server will take up to 12 minutes. Results will be displayed as a new web page. The results report will include the key inputs used and the outputs as graphics. After running, you have the option of cloning the run or deleting it. The main model outputs are soil temperatures and soil concentrations as color maps. The one on the left shows the seasonal nature of these soil temperatures for 3 years. The one on the right shows the initial contaminant concentrations used as inputs next to the color map, showing how this changed in time. These are other model outputs with additional ways of displaying changes in contaminant concentrations. The one on the left is the total depth integrated concentration at any given time. You can see how these degradation rates are not constant. The one on the right shows the estimated NSZD rates. These are the slopes of the depth integrated concentrations on the left. In this particular case, we also have field data. These are field measurements at a nearby location. These are coming from Natasha Sihora's PhD thesis. I have gained a deeper understanding of NSZD processes using this model. I hope others will find it useful. Some of the things you can do with it are refine conceptual site models. Is your site behaving as expected? Should you expect high or low rates given how much LNAPL there is? You can also predict the seasonality of NSZD rates. This model will help you understand the use of thermal gradients to estimate NSZD rates. This is an advanced topic worthy of their own discussion. Through BioTherm, I have gained an appreciation of the challenges of doing this and also some insight into how to do this quantitatively. You can test if providing supplemental heat will thermally enhance NSZD rates. Will passive solar work? How much will it cost? How much heat do you need to increase soil temperatures and enhance NSZD rates? Biotherm can be a tool to determine the design basis of such systems. Well, I believe with this introduction, you are now set to start your own simulations. We have provided a short list of simple cases to run. Feel free to try the advanced features once you have developed a familiarity with biotherm. Enjoy!